Progress.
Okay, guys, quiet, please. So for number 1 of the homework, it says write the mathematical limit. Sorry, the mathematical limit definition of the derivative. Blah blah blah. You know what's going on there. Write down 2 different notations, represent the derivative. Fine, like that's just copying from the notes, so I'm not too worried about that. In your own words, what does the derivative of a function represent? If you said the slope of a tangent line, that's good. It's an instantaneous rate of change. If you want to give like a physical example, like you're driving and the moment you're going 8 miles per hour, that could be like a derivative. So whatever you want to say is fine. 2 through 6, we're simply just finding these derivatives analytically. And they're asked different ways, like, hey, find f prime of x, find dy over dx, find ddx of x, find df over dx. Or saying, hey, find me the equation of the tangent line, which the slope of the tangent line is the derivative, right? Or find the equation of the normal line. You got to do the derivative first, and then do the negative reciprocal because the normal line is perpendicular to a tangent line. Find the slope of the tangent line, same thing. For 6, analytically determine the point on where that function of the tangent line is horizontal. Well, when the tangent line is horizontal, it's flat. That's going to be the peak of the curve, right? Or the low point of the curve. So in this case, I could just find the vertex and I got my answer. Or what you could do is find the derivative, set it equal to 0, and solve for x. That's actually what I prefer you do because it's a little more calculus related and it's more universal for any type of function. But since you're dealing with a parabola, you know the vertex is going to be your 0 derivative or horizontal tangent line. So here are the answers. These should be up in Schoology, I believe. So for number 2, the derivative is that. There's your tangent line. For number 3, the numerical value is 3. That's all they want, the slope of the tangent line. For 4, that's the derivative equation of the normal line. For 5, that's your equation. That's your derivative. And for 6, if you find the derivative, set it equal to 0 and solve for x, you get x equals -2. Plug negative 2 back in the original equation to get the y coordinate goes with it. So at -2, -5, that will be the tangent line that's where the tangent line is going to be horizontal to the graph. That's also the vertex too. It's also the vertex of the parabola. Same thing. So you're seeing more of these calculus connections to things you've done in the past already, right? So it's kind of good. Okay, so any questions on that at all? No? All right, and I think this is posted to Schoology. Let me look at that. Yes, Captain. Sure. Okay. I think it has. You need the homework too. No, I'm fine. Okay. Okay. Ready? All right. And again, solution keys are in Schoology. Good. All right. Close. Close. All right. So I'm not going to do, guys, quiet, please. I'm not going to do all this. It's just too much. But let's see how far we get. And right now it's 2:28. Okay, you have full day classes. I'm going to aim to kind of do a lesson for about no more than 40 minutes, I'd say. Let's see how we do. Anyway, differentiability, the ability to differentiate, right? Just a play on words. The ability to differentiate means you can find the derivative. Now, we did this already. We found the left-hand derivative before when we actually did the whole process of find LHD and RHD. So we call this LHD for short. We call this RHD for short. The RHD, of course, is 5. When they don't equal each other, it's not differentiable. I'll just abbreviate as DFF, DIFF. It's not differentiable at that value of X, right? We know this. Hopefully that all makes sense. And that's when we actually did this. And I don't know why I closed these notes. That was incredibly foolish of me. What was that? Oh, no. Here we go. That's my next extras. Yeah, thank you. Yeah. Hold on one sec, guys. Let me there we go. Yeah, so guys, remember this. We had these different formulas for the left and right hand derivative. It's really just the same thing as a derivative in general. But for the right hand derivative, h is approaching 0 plus, meaning you're approaching 0 from the right. So h is a slightly bigger number. So we have f of a and f of a plus h. F of a plus h, or a plus h, is a little bit more than a, right? Just a little bit more. So that's why we call it right hand derivative, because you're drawing, you have the point that you're interested, a comma f of a, you know, point a little bit to the right of it, and that tangent or that secant line, when it gets really close together, that's gonna be the right-hand derivative. The left-hand derivative is on the other side, right? So you have your point a comma f of a, then you have h is negative, it's less than 0, so it's 0 minus. So f of a plus h is a little bit, or f of a, sorry, a plus h is a little bit less than a. So you have that as well, and there you go. You know, that's your excuse me, that's your LHD, right? So that's how we calculate, in case you guys forgot. So now let's move on to example 1. And let's talk a little bit more about differentiability. So you got a piecewise function, f of x equals -1 when x is less than 0, f of x is equals 1 when x is greater than or equal to 0. Is it differential at x equals 0? This is the same exact thing as absolute of x over x. We've already looked at that function, right? Remember that function looked like this? So it's the same exact thing here. We have that. And we have that. It might be tempting to say quickly that the slopes to the left and to the right of x equals 0 are both 0. They are. They are. So the derivative is 0, but alas, we are wrong. We actually haven't found the correct one-side derivative in each case. Let's do that right now. And again, we need to go back to our formal definition of the derivative. F prime of a equals limit as h approaches 0 of f a plus h minus f a over h. Let's find the right-hand derivative. Let's find the left-hand derivative. And then we're going to connect this to continuity. This is a big moment. Page 2 is probably one of the most important things we do in this unit. Everything else, I mean, it's important too, but in terms of connecting differentiability and continuity, that really kind of ties it all again, closes a big loop, because continuity is needed for differentiability. I know I kind of ruined that moment for you because that's the moment on the next page, but we're going to connect this continuity very shortly because continuity is essential for differentiability. So let's do the right-hand derivative first, okay? So for the right-hand derivative, and actually just in the interest of time, I'll just show you the filled out notes. Sorry about that, and I'll just talk about it. I'm being a little lazy, my apologies, but this handwriting is much better, much nicer than mine. Here, let's focus on the right-hand derivative, okay? So here's the deal. Let me just talk about it. Okay, the way the piecewise function is written, in yellow is -1, and blue is, or turquoise, we're gonna call it, is 1. But more specifically, as f of x equals 1, we define it as x is greater than or equal to 0. So not just greater than 0, also equal to 0. So what is f of 1? Sorry, what is f of 0? 1, right? And what's, you know, and of course, -1 is when x is less than 0. So if you want to do this, the right-hand derivative, remember h is approaching 0 from the right side. So h is positive. So if I do 0 plus h, 0 plus h is positive, right? Well, when x is positive, which one am I going with? -1 or 1? 1. And of course, f of 0 is 1 as well. So what do you get? You get 0, right? So your right-hand derivative is 0. Just so happen that f of 0 plus h minus f of 0 are identical, right? Because again, h is positive, so a little bit more than 0. And yeah, get that. Okay. All's good? Cool. And my drawing was a little off, guys. I apologize. This was correct. I should have put a golden circle there. My apologies. That should be filled in. This 0 is included. It was a lot. Okay. Now, for the LHD. Now, for the LHD, remember, 0, sorry, h is negative. It's less than 0, right? Because we're approaching 0 from the left side. So, yeah, if that's going to be a negative number, f of 0 is still 1. We know that. But f of 0 plus h is going to be -1. Now it's -2 over h. Oh, that's interesting. Okay. And if you plug in 0 for h, that's a problem because it's going to be undefined. Usually, what happens, that's a vertical asymptote. Not usually, that is what happens. It approaches positive infinity if you were to check that out. If you were to plug in very tiny values for h, like say -0.001, something like that. You do -2 over -0.001, that's like 2000. You plug like negative like 0.00000 or -1 times 10 to the -20th power, so like scientific notation. Overall, this fraction is getting toward positive infinity. So here's the problem. The problem is the left-hand derivative is 0. Sorry, the right-hand derivative is 0. The left-hand derivative is infinity. They don't equal each other. When they don't equal each other, that's the definition of differentiability. The LH and RHL have to equal each other, just like for limits, you have continuity. The LHL and the RHL have to equal each other for continuity to exist. For differentiability to happen, LH and RHL have to equal each other, and they don't. So unfortunately, this is not differentiable. Okay. Oliver, go ahead.
So when you're finding a derivative of something, you can't just look at it. It's like looking at this line. It's like,
For piecewise functions, or whenever we have like a gap or some sort of like situation where like there could be a discontinuity or whatever, yeah, we have to examine a little more closely.
For continuous graph, could you?
Well, I'm getting there. Okay, I'll just hold on to a moment. Okay, so anyway. So sorry that this is a little busy. Hopefully you guys got most of it. And I'll make sure you guys have the fill out notes in school. I think they're there right now. Yeah. No, it's differentiable on both sides. It's just overall it's not differentiable. Yeah, I mean, kind of. I mean, I think what you really the right way to look at it, Duke, is you want to think of it as both LHC and RHC to be differentiable. You have to look at it that way. I think what you're asking, if I'm correct, is that does the derivative exist for the LH derivative? Actually, it really doesn't exist, because what is infinity, right? It's this abstract idea. So technically, LHC, there is no LHC. It doesn't exist. No, it's not. It's not. No, but what I'm saying is that we don't apply differentiability to one side limit. We apply differentiability to the combination of it. Oh, okay. So it's a combination to where we're different. We never say, oh, is it differentiable on the right side, differentiable on the left side? I mean, I guess you could say it's not differentiable on the left side if you want, but whenever you're being asked about differentiability, you're asking about at a specific point, looking at both LHC and RHC. So it's really looking at the big picture. So it's not differentiable because the left hand derivative is equal. That's exactly how you want to look at it. Yes, you be good.
So if zero wasn't part of like the positive one part of the equation, they would both be zero.
Well, you both would have like infinity or negative infinity, something like that. Well, actually, no, you can't do it because you don't know what f of zero is. Well, then if the point doesn't exist, and well, you can look at it. It doesn't exist, right? Right? Okay, so this is kind of the big moment. If f has a derivative of x equals 0, then f is continuous there. Also, if f is not continuous, actually, let's think of it this way. Let's start here. Let's start here. You'll see why I'm saying this. If f is not continuous at x, because that's true. For the graph we just had, that was totally true. Then f is not differentiable. So ignore this for now. Don't cross it off, because we do need that. But for now, just think of this. I probably should have put this first and put this on the page. Not confuse guys. But was it true? The problem we just did was not continuous, right? It was a jump discontinuity. And we just proved it's not differentiable. Okay. So now this is the part that's important. And this is using logic. And I'm going to do this onto the margins here. Very, very important. If you attend school in Atherton, then you attend a California school. Is that true? Yeah. Yeah, I'll call it statement A. Okay, statement B. If you don't attend a school in California, as soon as no other Atherton in the country, and actually, let me change that. If you attend Sacred Heart schools, Atherton, because there are a lot of different Sacred Heart schools in the country, right? Okay, let me change that up. Okay, statement B is what we call a contrapositive statement. So if this is the original, then this is called the contrapositive. Now, there's also the converse and inverse. I always get those mixed up. The converse, I believe, is if you swap. So these are if-then statements, right? So if I swap these two, but then it negates, if I just swap the two and said, if you attend school in California, then you attend Cigar School in no, you can go to Menlo, you can go to MA, go to Woodside, go to Pally, Gunn, a lot of the schools you go to. Just because you attend a California school doesn't mean you're here. So the converse is not necessarily true, right? How about the inverse? If I negate each one, but don't reverse the order. If you don't attend cigar schools and you're not in California, no, of course not. Again, you can get Menlo, MA, elsewhere, right? But this is true. If you switch and negates, if you don't attend a school in California, then you don't attend. That's always true. So you might have seen this before. If A leads to B, then negative B leads to negative A, right? You guys are familiar with this kind of logic? Have you guys seen that before? Like it's geometry, perhaps? I don't know. Does that make sense? Right? So if you think of it as something that's true, and then reverse and negate, that's true as well. That's exactly what's happening up here. I know this is true. We just proved it in the last page. So this statement has to be true too. Because what I just do, did I swap these two if-then statements? And then I said the opposite instead of not, got rid of the nots, right? That's true also. So what this means is that if you want a derivative, sorry, if you have a derivative at a certain point, guarantee you're going to be continuous. Guarantee you'll be continuous if you have a derivative at a certain point. And if you're not continuous, forget about it. No differentiability. So what will be true if f is not continuous at x equals a? We'll have a derivative. The answer is no. And why? Because again, because of the contrapositive statements. It all comes back to contrapositive logic. That's what's happening. Ron, good.
If it's not differential,
Of course, right. And you're not going to be continuous either. Actually, wait, let me take it back. Whoa, hold on. You just tricked me now. Okay. You can be continuous, so it's not differentiable. You can be. Okay. Yeah. Yes. But no, but sorry, but you're asking something else. That's my fault. I messed myself up. No, all you're asking was if derivative does not exist, not differentiable, right? That's all. Yeah, that's right. Okay. But you can have a point where the derivative doesn't exist, but can still be continuous. That still could happen. And so notice that we talk about contrapositive statements down below. So for example, if f is continuous, if f is continuous at x equals a, then f is differentiable there, right? If f does not have a derivative x equals a, then f is not continuous there. So it's pretty clear that at point A itself, or x equals a, sorry, but at a capital letter A, that's continuous, differentiable. This was kind of interesting. It's continuous but not differentiable. We're going to talk about that a little bit. Here, obviously, I have a discontinuity, so not differential there. But continuity is necessary for differentiability. The ability to differentiate got to be continuous. So logically equivalent statements, right? If P goes to Q, then negative Q goes to negative P. Okay. So let's do this one. Another example.
like double it.
Which two above it? Sorry. No, we're not talking about this. Are we doing the same? Yeah, no, if you're continuous, so I'm differentiable. Oh, wait one second. Oh, wait. Gosh darn it. I messed you guys up. Guys. Hold on. I messed you guys up. Guys, sorry. Okay, let's come back to this. No, you're right, Catherine. Okay. Okay, this is actually the converse, and I just meant if then F might. Yeah, sorry about that, guys. Erase that part. My apologies. Oh my God, I can't believe I did that. No, you're right. If F is continuous at x equals, it might be differentiable at, or might not be. And that's true over here, but not true over there. Because at sharp corners, you're not differentiable. And if you don't have a derivative, then F might be continuous. Or might not be. And where it is, at point B, but not at point C. So the bottom line is that continuity is necessary. For differentiability. You need to have continuity to make differentiability happen. And then again, we have these logically equivalent statements. And actually, I'll just kind of show the filled out version, just in the interest of time. Okay, it's not filled out. Never mind. Let me fill out really quickly. So we'll change this Mr. E.
No, because if you unless you don't put.
So if you're in my pre-cal BC honors class, guys, quiet, please. If you're in my E period pre-cal BC honors class, then you're student SHP. But that's true. So the counterpose would be this. If you are not a student at SHP, guys, quiet, please. Thank you. Then you are not in Mr. E's pre-cal BC honors class. And then converse is when you simply swap the two, inverse meaning negate. These are not necessarily true. Yeah, those are not necessarily true. Mhm. Right, exactly. It can be. Right, when you swap both statements and then you negate. And let's move on to example 2. Let's just move on. So the key idea, you have to establish continuity first, and then you can make a statement about differentiability. So in this case, are we continuous?
Not continuous.
So check for continuity. So first of all, does F1 exist? Totally, right? Yeah, good.
Why do you check the continuity to check the differentiability when you check the derivative?
Yes, but the thing, there's a moment. Okay, that's great question. Hold on to that thought. I'll get there. That's a great question because you may not be continued. Yeah, that's yeah.
You know, like in limits, if you don't have a code there, it doesn't matter what the limit. It's the same thing for differential.
Yeah, right, exactly. Yeah, so actually to answer your question, Oliver, what if you have something like this here? like you have a piecewise function where these are parallel. Each of the slopes will be the same, but it's not continuous.
But the derivative is this one.
So that's why just checking differentiability is not enough. We have to check for continuity to guarantee the differentiability part. So F1 exists, it does, right? What's F1? 1, thank you, thank God. And then the limit has to exist. Which it will. They are. And then lastly, F1 has to equal the limit, which it does as well. It does as well. Okay. So now we'll use our shortcut rules. For our left-hand derivative, we already did this in the previous notes, it's 3x squared. And for this one, it's just gonna be 1/3, just 1/3, right? Yeah. So I plug in 1, I get 3. Plug in 1 here, I get 1/3. The LHC does not equal to RHD. So we're not differentiable.
Yeah.
Exactly. Exactly. Yeah, so all three conditions worked for continuity, so we're fine. But the LHD and RHD are totally different. The LHD was 3x squared, plug 1 to get 3. Hold on, Carl. And then the RHD is 1/3 because you just take the slope of that line. They're not the same. Carl, go ahead. Because if it's not, then you stop. Then you don't even waste your time. That's why. You don't have to go through the motions of checking for differentiability. I mean, checking for LHD and RHD. That's why. Yeah, because the thing is that and actually I should have emphasized that. Yeah, then you already know differentiability cannot happen. So you can stop. Very good.
Like, do the derivative equal the same thing, or do they just equal the same at the point where you check the differential?
Well, they have to equal each other point of differentiability to be differentiable there. That's what you're
Do they have to,
investigating.
like, do the expressions of the derivative?
No. That's just the number. The number. Yeah. No, the expressions can be different, of course. It's a number. Okay, cases when you're not differentiable. Okay. So we have no continuity. Can you guys quiet, please? We're not continuous. Also, we have a sharp corner. Also, this is called a cusp. And this is called a vertical tangent. These are different situations where differentiability would not happen. And here's the reason why. Cusp. It's a cusp, sorry. Okay. Yeah, right. Okay, good. Yeah, crispy derivative there. All right, here we go. Okay. Okay. So sharp corners. This is when the LHD and RHD are finite values. But don't equal each other. Okay. Here, So a cusp, if you look at the left side, right? If you draw a tangent line, those tangent lines are getting steeper in a positive way. If you look at the right side of x equals a, those tangent lines are negative and getting steeper in a more negative way. Or it could flip. That's negative, that's positive on the left and right sides respectively. So that's why even though the derivative does not exist when it's inferior to negative infinity, we do want to be a little more explicit and know precisely what's happening, because that will tell us what to expect from the graph. That, okay, the graph's going to look like this, right? Because, and actually, this is a test question. I'll tell you right now. You know that one question I had where I gave you like some information about a graph and you had to make the graph? I know I didn't tell you guys that. I just kind of decided last minute I want to do that because I really love those questions. I'm going to do a similar question here where I'll say, hey, here's f of x. It's got a cusp. I'm not going to say it's cusp. I'm going to tell you the limit. The left-hand limit's this, right? Limit's that. And then you got to draw it correctly. But not like this, so not like what. No, but very similar. This gets derivative. Excuse me. Excuse me again. Now in this case, guys, quiet please. The LHD and RHD are both positive infinity. Okay.
I have a question. How did the two different sides for cusp touch if they're
They do touch.
slopes are they don't touch?
They do touch.
How is
This
it
is good one exists because if you draw a tangent line, it's gonna be straight vertical. They do touch. Oh, yeah, you're asking what's possible? If you do like x, remember we did power functions, I think, in the first semester, like x raised to the 4/5 power,
Okay.
something like that. That's how it looked. If you're asking how what equation would have, that's how it would form.
But like how do they touch if like if the slopes
Okay.
are infinity, won't they just keep going
Let
down?
me finish this. Let me get to your question. Because actually that question you're asking, we are not ready to do that until probably Wednesday or Friday. But I'll get your head a little bit because you're asking a great question. I know what exactly you're asking, how that can happen. Just give me a moment to finish this up, but I'll get there. So anyway, vertical tangents, they're both going towards the same slope, but it's positive and negative. Like in this case, as you get closer and closer to A on either side, the slopes are very vertical or very positive, here they're very negative. Okay. So to answer your question, Ario, let's go to Desmos. And I will be kind of getting ahead of ourselves a little bit, but it's okay because you're asking a great question. Okay, so there's a cusp. That's a cusp. Now, if I take that derivative, I'm going to tell you what the derivative is right now. It's going to be this. And by the way, this is the domain here is all real numbers, right? Because I'm just good rooting. Who cares? Plug in 0, I get 0, so it's fine. Now, I'm going to tell you I mean, there's a rule you can use. And again, we're not ready to talk about this rule until Wednesday. It's called the power rule. We did talk about it a little bit yet last week. So this is truly 4 over 5 times the 5th root of x. Now, here's the deal. If you plug in 0, what happens? It's undefined, right? When you're undefined, you don't exist. The derivative does not exist there because of what I just wrote. So also, if you were to plug in numbers very close to 0, like say 0.00000001 or negative 0.000001 or negative infinity, right? Because if I plug in negative, 5th root of a negative number is negative. So it's gonna be like negative crazy number and here's positive crazy number. So that's why that's happening. And they'll touch because the original function is fine at 0, right? There's nothing wrong with it. Plug in 0 into x to the 4/5 power. And also we understand why this works because remember we talked about like when you have power functions, when the x was between 0 and 1, it kind of has like a radical type of feel to it, right? And then if that's an odd, then it's gonna definitely exist on the left side because you can play negative numbers. But if that's an even numerator, it's gonna be an even function because it's symmetric about the y-axis. So that's why we spend all this time talking about even odd symmetry, talk about domains, stuff like that, so that we can make sense when we apply calculus to it. All right. See where we're at the notes. Okay, I feel pretty good. Let's do page 5, and then I want to stop there. Actually, let's just move to the middle of page 4. This is perfect. This is right in the middle of the notes, and we can finish off the rest of these notes on Wednesday. So this is perfect. Let's do this problem. Okay, so we're gonna do this without a calculator. I know we can do it. In case you guys didn't know, the square root of x squared is the absolute value of x. Okay, in case you guys didn't know. And I'm gonna write as a piecewise function because we should.
Wait, wouldn't it be just sorry, absolute value, it's not two absolute value?
Yeah, I did 2 absolute of x.
No, I'm asking why is it two absolute value?
Well, because there's a 2 here.
Isn't it greater than or equal to 0?
What was that? Was is that
I just.
oh, don't worry, it's Monday afternoon. You've had 3 other classes. You're all good. You're good.
Is it greater than or equal to
You know, we'll just put a grade. Yeah, it doesn't matter where you put it. Let's put it there. What the heck? That doesn't really matter. So it's gonna be 3x plus 1 and negative x plus 1. So if I do 3x plus 1 at 0, that's 1. And 3x. Just like that, right? And if I do this one, it's like that, right? So here's the deal. My LHD is negative 1. Am I wrong? No, it's 3x plus 1. Yeah, I'm right. Okay. So because these are both finite numbers, so in this case, continuity does exist because we see it. We see it happen. Continuity does exist here. It's 1 in each case at 0. So continuity exists, but RHD does not equal LHD, and there are finite values. Hence the reason for no differentiability at x equals 1 is due to there being a corner. That's how you want to say that. Yeah, they don't really do this so much on the free response anymore. They could. They tend to do other stuff, but you want to get in a habit of like justifying because they do have to justify for other free response stuff. But yeah, that'd be the reason. Yep. Ryan, go ahead.
I'm asking for differential at x equals.
Show it. Yeah, I did show it. Yeah, by showing the LH and RH didn't equal each other. I did show that. I mean, I didn't say it explicitly, I guess. I should have said that first. But the statement kind of takes care of it. The statement already told us that, yeah, RH is not equal to LHC, so we already know. But I'm getting a little deeper and talking about why, and that's because it's a corner, and that's when they're finite values.
Oh,
Okay, really quickly, guys. One last thing, then we're done. Most functions are differential where they are defined. Guys, quiet, please. Thank you. So whenever the domain exists, most likely you'll be like polynomial functions, differential is nice and smooth. I emphasize the word smooth. You need smooth curves to be differentiable. rational functions, even though there are infinite discontinuities along the way, or there can be, like poles or vertical asymptotes. But for the most part, we're all supposed to find that's fine. Grid, sine, cosine, no problem. Tangent might have discontinuities, infinite discontinuities, but secant, cosecant, cotangent. But for the most part, they're smooth. Log, they're smooth. Or if you combine all these, they'll be fine too. So for most part, you're going to see a lot of differentiability, but you know, piecewise functions, when we're being intentional and we don't want differentiability, you're going to see that piecewise functions usually. Just what's on deck, numerical derivatives. So I think I showed you guys how to calculate derivative in the calculator. I don't remember if I have done that. Have I done that yet? Yes. How to find the derivative. But we'll do that again. We'll revisit that. Actually, we did. And there's actually an algorithm it uses. We'll talk about that algorithm because it gives you an estimate actually. So we'll talk about that and we'll do it. We'll talk more about, we'll do more stuff in the calculator. This is kind of what we're talking about, like Ario had brought up, like that's to say we're not there yet. We will get there. But like, what if I took this derivative and seeing what happens there? I think that's a cusp again. The alternative definition of derivative is another way of writing it, so you should know that. We'll talk about that. And there's an IVT for derivatives, not just for just continuous functions, but for derivatives as well. And then on Friday, we'll talk about the test that's coming up, which I now move to Monday. And then once we do that, then the plan is to do, I think, up to section 4.1, if I'm not mistaken. Yeah, something called the chain rule. It does bum me out we don't do a bit more because there's a lot of cooler stuff that comes down the pipeline, but it's not part of the class, so be it. So we'll do 4 more sections when we so looking at the calendar again. So yes, Wednesday we'll finish 3.2, review a test Friday. May 1st we'll do 3.2. Then 3.3. Then 3.4. Then I think 3.5, then 4.1. I might need a couple days for some of these here. The plan is to have our test on the 15th if we can have it, or the 17th. So after that, then we review finals. And the finals on the 28th. And some of you guys, I assume there's a lot of AP students in here, like A push, right? There's some A push. Juniors, well, sophomores only do A push though.
Computer science.
Oh geez, okay. So you guys are gonna be pretty busy. So we might have some of you guys might be missing class. You all have videos, all that stuff. So anyway.